So here you notice this, when the program ended, it had that much memory taken up. It was almost the full memory because I'm really pushing this on memory. And then as it's initializing, it's getting more and more memory taking up because that's where the particles move into new cells and they have different, the cells expand to accommodate them.
Does the cell ever shrink?
No, I haven't added that because we don't have enough molecules. We don't have enough memory for enough molecules where that would be a huge problem. So here you notice I'm printing out the time it takes for each thing to happen. The rearrange time, that's the single core part, took 0.22 seconds over 20 time steps, and the calculation time was about 4.5 seconds. And so if I change this to 1 core, then you'll notice it's a lot slower. Guess why? Because it has it's only on 1 core. The memory's going up more slowly, and I'll show you calculation time. Calculation time is 8 seconds. So it's not linear, but you can see there's an effect there. So anyway, we're going back. So in the future, I might want to put in more sophisticated objects because most of the time when you're designing a spacecraft or something, you'd be doing it in some other program, and it'd be nice to just be able to import that. It'd be nice to have adaptive cell meshes, which I have no idea how to do because that would be really difficult. Essentially, you adjust the size of your cells so that denser regions have more cells in them so that you preserve accuracy.
And we'd also like to look at more of the chemistry reactions. So we might have rotational freedom, and we might have actual chemical reactions between particles. We were looking at charged particles, because right now we only have a neutrally charged particles, so we might have ionization.
And I'd also like to look more into how we can make this work on multi-core processors or on other things like GPUs, graphical processing units, because there's a lot of, these are both new architectures for applying DSMC to, and it'd be interesting to see that. And the current work with multi-core, I haven't seen any papers out there that talk about how DSMC runs on multi-core. So that's a new thing that I've done, and I'd like to continue that. That'd be interesting. So in conclusion, we have a DSMC model that's correctly calibrated for simulations in the upper atmosphere, and we verified it through a series of tests. We've also looked at its efficiency on multi-core, and we found that it's a good demonstration of the slowdown, the bottleneck in multi-core architecture. And we found that our model can be applied to a variety of objects in the upper atmosphere and give us a lot of data about how they're moving through.
Questions? Yes.
It looked like a number of the objects you were modeling were symmetrical. Did your code actually compute both sides?
Yeah, and we have asymmetrical objects too. It's just the symmetrical ones are the interesting ones. Right. So those are the ones we showed. We do have asymmetrical ones too. Okay,
well that would cut your...
Yeah, when I was first doing the box simulations, I just simulated half. And then, okay. So yeah.
So this is the DSMC is computationally very intensive. Mm-hmm. Relatively simple algorithm, actually. And you can run it fairly easy on multiprocessors. What are the competing algorithms? Is there any other model, a partial differential equation or something like that, that would require less compute power and maybe not be so easy to parallelize?
Not for upper atmosphere.
So, well, one of the advantages of DSMC is we can simulate a larger region. So we sacrifice some of our complexity, but we have a much larger region we can simulate with more particles.
And the reason, we can't use, we could use molecular dynamics, and we could, laboriously trace the trajectories of these particles that are meters apart, but it just doesn't, it's worse. This is the best model for upper atmosphere where it's rarefied.
So I'm interested more in the physics, which is so you're talking about that this technique is valid for a low density, right? So what is the range of value on low density? Like 10 to the minus 3 to 10 to the minus 5 or to 10 to the minus 10 air particles per centimeter cube, or what is the range?
So, well, it depends on the Newton number. For example, we could use DSMC to simulate in this room, but our object would have to be smaller than the mean free path, which is like almost 0. So it totally depends on the size of your object.
With
So, but what are you using here on the spacecraft simulation?
We ran these simulations at 90 kilometers.
No, but the density.
I think.
Density
10 to the
at
minus
90
7.
kilometers.
I believe it was 10 to the minus 7.
I have that on in our program. Oh, never mind. I guess I didn't copy that down. Pressure is this, which is not very much.
The mean free path is about 2 centimeters.
So my concern is that, Cliff was asking about what are the other options? And the other option is a smooth particle hydrodynamics and a plain Monte Carlo. There are several other options. Here, you mentioned that it's valid for a rarefied gas. But what happens in the areas around the spacecraft? You show the map of the density around there. What is the
higher.
density? It's high, right?
Right, which is why
So-
you'd like adaptive cell sizes.
That's what the one is, or you adapted.
We don't have that,
He'd like to
but it'd be
But
nice.
you have, yeah, because most of the problem the SPA has, and they report the instability because of that, and there was a previous presentation here that also showing instabilities. But this one, at least in the way you have shown it, you don't show any stability yet, for the timing. Like for example, if I ask you, for how long you have run your simulation, like hours, how long has your space has traveled? It has traveled the full 300 kilometers or 100, or just traveled a few meters.
Our space, in the simulation we showed, the time we took to calculate was, darn it. It's like a fraction of a second because it took for 15 minutes. But when I run these at home, I run them overnight or over a couple days, and I simulate a couple seconds. And that's because we have a quad core. We don't have a supercomputer.
So that would make a difference.
So what is your time step?
Time step is 0.0000679.
We do our time steps, so we calculate about 1/10 of the total collisions in
It's
one
that.
time step. That's how we.
50,67698. I was
Of a
close.
second.
So, quick, just quick.